Welcome to MathGPT. In today's lecture, we're going to review differential equations, one of the most powerful tools in mathematics for modeling real-world phenomena. Whether you're studying engineering, physics, biology, or economics, differential equations provide a way to describe how quantities change over time. Let's start with some basic definitions. A differential equation is an equation that relates an unknown function to its derivatives. For example, this is a simple differential equation where y is a function of x and dy by dx represents the derivative of y with respect to x. The order of a differential equation is the highest derivative that appears in the equation. This is a first-order equation because it only involves the first derivative. And this is a second-order equation because it involves a second derivative. Now, let's talk about the different types of differential equations. One way to classify differential equations is by whether they're ordinary or partial. An ordinary differential equation, or ODE, involves derivatives with respect to just one independent variable, like x. A partial differential equation, or PDE, involves partial derivatives with respect to multiple independent variables. Another important classification is whether a differential equation is linear or nonlinear. A linear differential equation has the property that the dependent variable and its derivatives appear only to the first power and are not multiplied together. In contrast, a nonlinear differential equation might have terms where the dependent variable or its derivatives are raised to powers other than 1, or they might be multiplied together. Now, let's discuss solutions to differential equations. A solution to a differential equation is a function that satisfies the equation. For an nth-order differential equation, the general solution contains n arbitrary constants. A particular solution is obtained from the general solution by specifying values for these constants, usually through initial conditions. An initial value problem consists of a differential equation together with enough initial conditions to determine a unique solution. Now, let's review some methods for solving first-order differential equations. The first method we'll discuss is for separable equations. A separable equation can be written in the form where we can separate the variables, placing all terms with y on one side and all terms with x on the other side. For example, consider the equation dy by dx equals x times y. We can rewrite this as dy over y equals x dx. Integrating both sides gives us the natural log of the absolute value of y equals x squared over 2 plus c, where c is a constant of integration. Solving for y, we get y equals e to the power of x squared over 2 plus c, which we can rewrite as y equals k times e to the power of x squared over 2, where k is e to the power of c. Another important class of first-order differential equations is linear equations. A first-order linear differential equation has the form dy by dx plus p of x times y equals q of x. We solve this type of equation using an integrating factor. The integrating factor is e to the power of the integral of p of x with respect to x. Let's solve the equation dy by dx plus 2x times y equals x. First, we identify that p of x equals 2x and q of x equals x. The integrating factor is e to the power of the integral of 2x dx, which is e to the power of x squared. Multiplying both sides of the original equation by this integrating factor, we get e to the power of x squared times dy by dx plus 2x times e to the power of x squared times y equals x times e to the power of x squared. The left side simplifies to the derivative of e to the power of x squared times y. Integrating both sides, we get e to the power of x squared times y equals the integral of x times e to the power of x squared dx. Using integration by parts, we find that e to the power of x squared times y equals 1/2 times e to the power of x squared plus c. Solving for y, we get y equals 1/2 plus c times e to the power of negative x squared. Here's a graph of this solution for different values of the constant c. Now, let's move on to second-order linear differential equations. A second-order linear differential equation with constant coefficients has the form a times d squared y by dx squared plus b times dy by dx plus c times y equals f of x, where a, b, and c are constants. When f of x equals 0, the equation is called homogeneous. When f of x is not 0, it's called non-homogeneous. To solve a homogeneous second-order linear equation, we first find the general solution to the homogeneous equation. We do this by finding the roots of the characteristic equation, A, r squared plus b, r plus c equals 0. If the characteristic equation has two distinct real roots, r1 and r2, then the general solution is y equals c1 times e to the power of r1x plus c2 times e to the power of r2x. If the characteristic equation has a repeated root, r, then the general solution is y equals c1 times e to the power of our x plus c2 times x times e to the power of our x. If the characteristic equation has complex conjugate roots alpha plus or minus I beta, then the general solution is y equals e to the power of alpha x times c1 times cosine of beta x plus c2 times sine of beta x. Let's solve an example problem to tie everything together. Consider the differential equation d squared y by dx squared minus 5 times dy by dx plus 6 times y equals 0, with the initial conditions y of 0 equals 2 and y prime of 0 equals 1. First, we find the characteristic equation, which is r squared minus 5, r plus 6 equals 0. Factoring this equation, we get r minus 2 times r minus 3 equals 0, which gives us the roots r equals 2 and r equals 3. Since we have two distinct real roots, the general solution is y equals c1 times e to the power of 2x plus c2 times e to the power of 3x. Now, we use the initial conditions to find the values of c1 and c2. First, using y of 0 equals 2, we get c1 plus c2 equals 2. Next, we find y prime of x, which equals 2 times c1 times e to the power of 2x plus 3 times c2 times e to the power of 3x. Using y prime of 0 equals 1, we get 2 times c1 plus 3 times c2 equals 1. So we have the system of equations, c1 plus c2 equals 2, and 2 times c1 plus 3 times c2 equals 1. Solving this system, we find that c1 equals 5, and c2 equals negative 3. Therefore, the particular solution to our initial value problem is y equals 5 times e to the power of 2x minus 3 times e to the power of 3x. Let's graph this solution to visualize it.